Hello and welcome. This is section 7 of chapter 1, Physics 313, a short section, more conceptual, but still also very important. That is an overview about solving problems in physics. It starts off by saying that careful planning and design needs to be taken into place when undertaking a large project. And that's absolutely true when we're solving physics problems. Granted, the problems we'll be solving at the beginning of the semester, it's easy to, especially for folks that have had previous physics before, to just want to jump straight to the answer, or to try and jot down some half-remembered formula from high school, or just try and quickly get the answer as quickly as possible, plug it in, move on. I would highly encourage folks, no matter what your level of previous physics is, to commit to these techniques and strategies to develop good problem-solving techniques, because when we get to later problems in the semester, or even in physics 2, so highly complicated electromagnetic problems, drawing a picture, these verbal and pictorial and mathematical and graphical representations are essentially critical. And really looking further, any of the modern problems in physics, I'm talking about modern in the sense of problems that we're facing right now, in 2020, 2021, these problems need lots of planning, lots of care, and lots of design, and you want to be able to present this information to what we call key stakeholders, whether that's the people that you're trying to, general public, or whether it's regulating body or funding agency, any of those pieces. So we want to make this information as clear as possible, and that's part of the training of this textbook. So several different ways to represent these situations. We have the verbal representation. Okay, well, the verbal representation is sort of the verbal representation is really just the words of the problem. I mean, more or less how the problem is stated. And then we have the pictorial representation. That involves a simple sketch, motion diagrams, symbolic representation of parameters. Then we have a graphical representation if it's necessary, including position, velocity, acceleration versus time graphs. Oftentimes other different types of graphs will show up later, involving force and momentum and energy where they're appropriate. So that will change from time to time. And then finally, mathematical representation. Mathematical representation is how ultimately we want to translate all of this words and pictures and graphs into something mathematical that we can then solve. And while this, again, isn't necessarily for the problems that we do in this class, I would even argue that, another representation would be kind of an algorithm representation of how you're going to solve, the problem, because oftentimes modern problems involve, intense computer simulations. And so that's also important too, just how to logically structure the problem. So let's go through some of these in detail. Okay, so what's the first one? Drawing a pictorial representation. Okay, so what all is part of an official pictorial representation for these problems in physics? Well, it looks like the first step is draw a complete motion diagram. So the complete motion diagram was in section 1.6, including that, of course, includes coordinate system, origin, position of the dots, velocity, and acceleration, all in a motion diagram. This is something that the first starting out to understand what the type of motion is. And of course, this the coordinate system, it'll be used not only for the motion diagram, but also for kind of a quick sketch, right? You can choose either the X or the Y axis. Of course, that will depend on the context. This book will also use the generic S, as in Sam, S axis, to denote axes that aren't necessarily horizontal or vertical. We'll deal with problems on inclined planes, and so an S axis will be a more conventional way to write things as well. Okay, so motion diagram and then a coordinate system that we established. It's pretty clear. Some problems, it might not be clear where you want the origin. There might be one or two choices. For instance, if you're doing a problem where you're approaching a stop sign or you're approaching a red light, and you're moving. Where do you want the origin? Well, do you want the origin to be at the stoplight? Okay, well, that'll make your positions negative or positive. Or do you want it at the start, where you're at? Those types of considerations. Third step is sketch the situation. And yeah, several things to remark about the sketch. Obviously, it doesn't need to be a work of art. And it needs to be something simple enough to where you understand what's going on. My cars that I draw in lecture, they're very simple. They're little ovals with little circles on them representing the cars. You know, or the rockets, draw simple rockets, get good at drawing these stick figures. But the important thing is that you need a beginning, at least a beginning and an end, when you only have one type of motion. But if you have instances where they call it the character of the motion, or sometimes called the state of the motion, where that changes, you want to include that position where you change the state. For instance, if you are doing a problem where you start from rest at a stoplight and then you accelerate to reach a top speed and then maintain that top speed, well, you would want 3 different pictures of the car, 3 different instances of the car. The car when it's at the beginning at rest, the car when it reaches its top speed, and the car at the end after it's continued with that top speed. So when the state of the motion changes, you want to redraw the figure. Some of these questions in chapters 2 and so on may have more than one changes in motion. For instance, an elevator, right? You're starting from the ground floor of an elevator in a skyscraper. You increase speed to reach your cruising speed, and then you maintain that cruising speed, and then you slow down. Well, you would need 4 different figures of the elevator. So sketching the figure, it's very clear, very simple, and oftentimes just using really basic shapes. Okay, so continuing with what else we need for a pictorial representation, define our symbols. Now this is important because these are the things you'll use when you do your equations. This will make it as clear as possible. So you want to attach what I call position, velocity, and acceleration timestamps to each picture that you draw. And use subscripts too. The book in the equations will use a lowercase I and a lowercase f to indicate initial and final subscripts respectively. But when you do the pictures, when you do your problems, you don't want to use initial and final. Why? Because exactly what we were just talking about. When the state of the motion changes, then your final would now be the initial for the second part. That's too much confusion. So instead of doing initial and final, use numerical subscripts. The very first instant is, by convention, a 0 subscript, sometimes called a naught, N-A-U-G-H-T, a naught subscript, like X naught, T naught, or V naught X, those types of things. And then continue with 0, 1, 2, and possibly 3 if you need to. But we will always define, so we're always going to define a position, velocity, and acceleration, or sorry, a position, time, and velocity for each instant. And then we want an acceleration between those instances. So it mirrors the motion diagram of where the accelerations occur, but there's always one less acceleration given how many timestamps of position, time, and velocity you have. That's defining symbols, and that's what you use in the mathematics. And then finally, also important, list all known information you can think of in a little table, and then identify the unknowns and put that separately. All these things help you get nice and organized when you're trying to solve a difficult physics problem. And so this, the problem-solving strategy for these one-dimensional problems, the pictorial representation fits into it. And so we have all of these different steps, okay? We've got the model step, the visualize step, the solve step, and the assess step. So, and this is with problem-solving strategy for any types of problems, whether it's forces or energy or momentum or rotation or pressure, any of these fun topics we'll get to later. So model. Unless explicitly stated, we'll probably be using the particle model for the first 11 chapters, okay? Ignore every detail of the situation, simplify the situation. Oftentimes this gives students the most trouble of figuring out how to simplify it. The only model we have so far is a particle model, and all the equations over the next several chapters will follow from the particle model. But there's also the rigid model. There's the wave model. There are plenty of different models that we'll see. There's the thermodynamic models. And the next thing, visualize. So models, the first step in the general problem solving strategy. The next one's visualize. Right now we want to use, this is where we draw our pictorial representations. We just used previous text box for that. And solve. Solve is where we identify the mathematical expressions that correspond to our model. Okay, the solve step is really what we break apart in chapter 2. We assign different mathematical equations that are associated with these specific models. And we're only going to have 2. We're going to have uniform motion, we're going to have constant acceleration. So we make a mathematical representation of the problem with the symbols that we defined. And then once we've done that, now we can go through the algebraic manipulations, sometimes do calculus also, use all our mathematical tools to solve the problem. And we will be using a lot of them. In addition to basic linear systems of linear equations with 2 equations, 2 unknowns, we'll also have calculus examples, we'll have natural logs, we'll have exponentials, we'll have vector algebra as well. So lots of different mathematical representations. There's an assess step, which is often easy to forget. Does your answer make sense? Okay. If you are talking about velocities of a car, if you get 0.03 miles per hour, that probably doesn't make much sense. At the same time, if you get 700 miles per hour, that probably doesn't make much sense either. And for these everyday examples, most of these problems will be kind of examples that you can kind of visualize from your previous experiences. That assess step is very helpful. It's hard to put some context into parameters like gravity, like when you calculate the mass of an unknown planet, doesn't make sense. Well, that's when you need some intuition from previous data that you've kind of looked at. So those are the 4 steps, the general problem solving process. And of course, we have a full example here that does everything. It doesn't actually solve the problem, but we use the first 2 steps of the problem solving strategy to model, analyze, and visualize the problem. So we're launching a rocket, okay, with initial acceleration, 30 meters per second squared, about 3 times that of gravity, runs out of fuel at 30 seconds. What is the maximum altitude? So that's a typical problem, and you would define all your symbols, and what would the sketch be, right? The sketch would be the simple rocket, how you draw a simple rocket, right? I mean, simple rocket is just a long kind of tube upward, right? And you can make the little flares at the bottom. Let's see what they have in the example. So, and they even have it in this sort of handwriting type, description to make it look more realistic. So this is a perfect example of how important motion diagrams. So start and stop, fuel runs out, that's helpful. We got plenty of dots, and then we have our coordinate system. They have the little flares for the rocket, but we have our timestamp, our y sub 0, our v sub 0 y, and our t sub 0 at the bottom, and then then a sub 0 y. And then when the fuel runs out, we have the y0, we have the y1, we have the v1y and the t1, and the same thing at the very top, y2, v2y, and t2. When you're doing strictly one-dimensional problems, the y subscript in the velocity and the acceleration can be omitted because there's no chance of confusion. Now, when we get to projectile motion problems, launching a cannonball off of a cliff, yeah, we do need to include those because those are separate. And then we've got a place where we list all of our knowns. That's the fun part because you just get to look at what you have and and write it all out. Most of them are 0. And sometimes you can even make, like we see at the bottom here of that list of knowns, sometimes you can even make estimates on, you may not know a specific number, but you actually know the sign of it. So include what the sign is. And unknowns to find, what are we trying to find? In this example, of course, we're trying to find the maximum height. So this is all of the first couple steps of the problem solving strategy, the model step and the visualize step, where all of this is what the book argues is included in a visualize step. So, and although this section seems like it's kind of not as important because it doesn't have new physics content in it, it really is one of the most important ones when you're solving the problems. So try to be clear with this pictorial representation. Okay, so that is the end of this section. The next section on units and significant figures will be the final section. It includes a couple of important things and some things that are actually unique to this textbook that Mastering Physics will complain at you for when you do the questions. So stick around for that last final video. Thanks for your time as usual.